Okay, the last part for proteins is talk about some functions of proteins, in particular talk about enzymes. Okay, enzymes are biological catalysts, so we need to define what a catalyst is first. A catalyst is a substance that increases or speeds up a chemical reaction, and without itself being consumed in the process. Okay, what it does, the catalyst, what it does is it increases the rate of reaction or speeds up by helping the process along. And when it does that, it lowers the energy required for the chemical reaction. And this energy that's required for a chemical reaction is called the activation energy. Let me talk about the activation energy for a second. So let's say I have a piece of paper, and the piece of paper, it's really not in its natural state. The paper would much rather turn into carbon dioxide and water than stay paper. That's really what it would rather do. So when you have a piece of paper, it's just sitting there basically going, I wish I were carbon dioxide and water. Okay, but why isn't it then carbon dioxide and water? The reason why it's not carbon dioxide and water is because it has to get a kick. Something has to happen to have it help it along to turn it into carbon dioxide and water. It needs a kick, just like in the morning when you get in bed. All right, it's just that it's like your alarm clock. When your alarm clock goes off, that's your kick to get yourself going for the rest of the day. So the activation energy is like the alarm clock. So for a piece of paper, what is the alarm clock? What gives it a kick? Maybe it's a spark, just a tiny spark. If you take a tiny spark and put it to paper, it'll cause paper to burst into a giant flame, and when it does that, it turns it into carbon dioxide and water, just like it needs. Now, all chemical reactions need a kick. They get going. Some of them need a really big kick to go in it. Actually, paper needs a fairly big kick. You need to get a flame to get it going. Okay. Some chemical reactions hardly need any kick at all. Like if you had some nitroglycerin, which is explosive, all you have to do is drop it and it goes kaboom. So the only kick it needs is to be dropped on the floor. Okay, and that kick is called an activation energy. And what I have here are technical stuff. Okay, blah blah blah. Okay, and so what catalysts do is that they reduce the size of that energy so that it's easier for the chemical reaction to take place. You don't need as much energy, you don't need much heat for the chemical reactions. Most of the chemical reactions that take place in our bodies require a lot of energy. But what enzymes do, or biological catalysts, is they they reduce the amount of kick that is needed to do the reaction. So you don't need a lot of temperature for the reaction to take place. So we don't need to be on fire to burn glucose. If we didn't have enzymes, we would have to be on fire to burn glucose, okay? To burn fat, to burn glucose, okay? But we don't need to be, because of the enzymes. What they do is they kind of reduce the required amount of fire for the reactions that take place. All right, and here's the diagram. So the purple may be, so I have this reaction of carbon dioxide and water, and it turns into carbonic acid. It's just some chemical reaction, you don't have to know it. But what you usually need a big kick to get it going. It has to go. You have to kick it way up in the air, and then once it gets up there, then it'll come flying down. But what enzymes do is they lower that hill, so it's easier to go over it. You don't need as much heat. You don't need as much temperature for that reaction to take place, and that's what enzymes do. Okay, just give some ways to identify enzymes by names. Enzymes will usually end in ACE, and I'll give you a couple examples. We've talked about them in class when we talk about carbohydrates. But there's some that end in IN. But mostly notice if you hear ACE, you have a enzyme. Remember OS with sugar? Okay. I mean, we've had other things like oic acids and anes, Ls, ols, ons, als, etc. Now you have aces. Right? And usually the name refers on what it's working with. And we talked about a couple of these already. We talked about sucrase, which breaks down, is an enzyme, ends in ACE, and what it does is it breaks apart glucose and sucrose into glucose and fructose. We talked about lactase, that breaks apart lactose into galactose and glucose. And we talked about maltase, which breaks down maltose into two glucoses. We talked about the chemical reaction of oxidizing alcohol to acetaldehyde. It's like if you're going to drink some alcohol, your body breaks it down to acetaldehyde. Normally that takes a lot of energy to do, but our bodies have an enzyme called alcohol dehydrogenase, which makes that reaction take place quite easily. Now, if you remember the chemical reaction, what happens when alcohol turns into acetaldehyde is two hydrogens go off. So what you do is you take alcohol, remove hydrogens, dehydrogenase, and it's an enzyme. Okay, so what we're going to do is talk about actually how enzymes work now. So enzyme activity. Okay, so there's three parts. There's the enzyme itself, and then there's the substrate, which is the thing that's going to be turned into a product. So substrate is also known as the reactant. Okay, they call it substrate because it combines with the enzyme. A substrate technically means a combiner. So a substrate is a reactant. What it's going to do is combine to the enzyme. And where it binds is very specific. It binds to a place called the active site in the enzyme. And when it binds to the active site, chemistry gets done, and then you form product. And we're going to walk through how this takes place. Right, so this is just a picture of what it might look like. So you have your substrate and your enzyme. The substrate binds to the active site, which is very specific for a substrate. This enzyme will only work with this substrate, and it will only form this product. So for every chemical reaction, there is a particular enzyme, a particular substrate, a particular product. So the substrate binds to enzyme, chemical reaction takes place, forms product. Okay, so let's walk through what happens in enzyme. Okay, so what you have first, you have the enzyme, the active site, and a substrate. Now, this enzyme will bind specifically to this shape of substrate. So this guy will fit right in there. So the first step is the substrate and the enzyme combine, and then they bind. Okay, and what we mean by bind is they form connections. So and that's to lock it into place. So the enzyme and the substrate are docked together, and now what we can do is do the chemical reaction. Once it's locked in there, what happens is the enzyme will twist and turn to change the substrate to something called the transition state, and it's this orange blue thing. Okay, and we'll talk more about why this transition state is important. Okay, so once it makes that transition state, the chemistry takes place. And then what happens is some energy comes in here and then turns it into the product. So the chemistry doesn't happen until we get here. All right. So this first step is it binds, twists and turns into this transition state. And then you get the chemistry where it actually turns the reactant into the product. So what the enzyme has done is pushed the substrate to the top of the hill basically a lot easier than it's basically made the hill a lot smaller by making this transition state. And then once it makes this transition state, energy comes along and turns it into a product, and the product goes off. So if you notice, the transition state looks a little bit like the substrate at the beginning and a little bit at the end. So what the enzyme needs to do is turn it into a piece, something that looks somewhat in between. Now, why does it need to do that? Okay, here's the reason why I need to do that. So here's a normal chemical reaction. So you need to push it up this hill, and then it comes flying down. Well, actually at the top of this hill is this transition state. Okay, so what the substrate has to do is turn into this transition state. Once it turns into this transition state, it'll turn into the product. What an enzyme does is it makes the transition state without going all the way to the top. So the enzyme makes the transition state at a way lower energy than is required without the enzyme. So what the enzyme does is it makes the transition state at a lot lower energy, and then then you just need a little bit of energy for that reaction to take place. So the job of the enzyme is not to do the chemical reaction, but is to make the transition state at a lower energy so that the chemical reaction can take place. Okay, going back to how does a substrate lock into the active site? Well, it can lock in through same kind of interactions we've talked about before: dipole-dipole, London dispersion forces, and hydrogen bonds. And these are all temporary interactions. Just they're held in here long enough for the chemical reaction, to the making of the transition state, and then the chemical reaction. Okay, all right. Sometimes some enzymes need some help. And the helpers are called coenzymes. And what coenzymes do is they will bind to the enzyme, and then when they bind the enzyme will become better at what they do. And here's an example of a coenzyme. So here's your enzyme. Coenzyme connects in here. Then once it connects there, the substrate can come in, and then the enzyme can make the transition state and then finally make the product. So some enzymes need coenzymes. Now, coenzymes, there are two different kinds of coenzymes. One are vitamins, another are called minerals. So when you take vitamins, what vitamins get turned into coenzymes, and the coenzymes will connect to the enzymes that they are needed. So like vitamin B turns into a coenzyme that will interact with some enzymes that help break down glucose. Okay, now what we're going to do is talk about 4 different factors that can affect how fast a chemical reaction takes place. Okay, one of the things we're going to talk about enzymes is, you kind of got to think about enzymes as like a factory or workers, and substrates are parts. And so what the what a worker does is a worker will take some parts, take those parts and make a product. Okay, they might take a bunch of plastic pieces. A worker might take a bunch of plastic pieces, put them together to make a toy. Okay, the plastic pieces would be the substrate. The toy would be the product. The worker is the enzyme. So let's start out with that first. Okay, in the first case is one way you can speed up a chemical reaction using enzyme is to add more workers. So enzyme concentration means workers, increase in workers will increase how fast it goes. So if you have more workers, you get more particles, more product. So if you want to speed up a chemical reaction, you add more enzymes. Okay, that's if you have enough parts. Okay. Now, this one case is the following. Let's say I am a worker and I can make 5 toys in 1 minute. Okay, so my boss comes by and he gives me enough parts to make 1 toy. And he says, I'm going to come back in 1 minute and see how many toys you have made. Well, I hope you could see if I have the ability to make 5 in 1 minute. If he gives me the parts to make 1 in 1 minute, I will be able to make 1. That's easy. All right. He goes, wow, okay, you're pretty good. So he doesn't know how fast I can go. Comes by and he gives me 2, enough to make 2 toys. And he says, I'll come back in 1 minute and see how many toys you made. Okay, comes back, well, I can make 5. I come back and there's 2 sitting there. All right, so let me show you how this relates to this graph. So subconcentrate is parts to make toys, and this is the amount of toys I make, reaction rate. So if he gives me, so far gives me 1 toy, I can make parts to make 1 toy, I can make 1 toy. He gives me parts to make 2 toys, I can make 2 toys. All right. Now he comes by and gives me 3 parts to make, parts to make 3 toys. Comes back in a minute, I can make 3. Make what 8. And he comes back, gives me to make 4. How many can I make? 4 toys. And then he comes back and he goes, oh, you're pretty good. Let's see, how about 5? So he gives me the toys to make 5, to make 5 toys, and parts to make 5 toys. Comes back and I got 5 toys. Right. Then what he does is he goes, okay, what I'm going to do is I'm going to give you the parts to make 6 toys. And he comes back after a minute, how many toys have I made? I've only made 5 toys. That's because all I can do is make 5 toys per minute. And he comes back and he gets to have 7, make 5. And so that's what this graph shows me, is that I can go as fast as I can go. So if I can only make 5 toys per minute, I can make 1 per minute, 2 minute, 3 minute, 4 minute, 5 minute. But if he gives me more, I always level off. I can never make more than 5. And that's what enzymes can do. Enzymes can only go a certain speed. Okay, it doesn't matter how much parts you have, they'll go at speed. Now there's a kind of funny video that I have here that you can take a look at. It has to do with Love Lucy, where she's working in a chocolate factory. You've probably seen it maybe, where her and Ethel are working on making packaging these chocolates, and the same kind of thing. The assembly line starts out slow and they got really easy, and then it starts to speed up, and they realize it's that they can't do as many as they can. So for this type of, there's two different types we have. We have the first type is you can speed up a chemical reaction with enzyme by adding more enzyme. Another way you can speed up a reaction is add more parts. Okay, so what we're doing, so you can add more part, that increases the reaction, but there's a limit to that. Okay, this is that you can keep adding parts, but the enzyme can only move so fast. So you can increase the speed of enzyme by adding more enzyme or more substrate, but if in terms of the adding more substrate, there becomes a limit on that. Okay, all enzymes have a specific temperature they work at. For us, it's 37 degrees Celsius, which is 98.6. If it gets too hot, our bodies won't be able to work as well because the enzymes start to fall apart. And if it's too cold, our enzymes can't work because they get stiffened up. So there's an optimal temperature that all enzymes work at. And usually it has to do with the organism's specific temperature that it lives at. Okay, another way to think about enzymes is they all need to be at a specific pH. So if the pH is too high or too low, the enzyme won't work. Okay, there they go. pH values of your fluids in your body can be different. Now, in your blood, there are chemical reactions taking place, and those chemical reactions have to take place around 7.35 and 7.45. And as a nurse, you will learn about this. Now, if it gets too high or too low, then the chemistry in your blood can go wacky, and then you can have some serious problems. So what your body does is it produces these things called buffers, which help keep the pH of your blood constant. Okay. And so you may learn more about this in your nursing program, these blood buffers. Buffers are not enzymes. What they do, they're chemicals that help to keep the pH constant for the enzymes can work better. All right, so here's two examples of two enzymes that do the same job. That means they chop up proteins. They're found in two different places, and those two different places have two different optimal pHs. So both of these guys, pepsin, trypsin, do the exact same job, but they do them in different environments. If you took pepsin and put it in your small intestines, it would not work because the pH would be too high, and vice versa. Okay, just a couple more things here. One is called enzyme inhibition. An enzyme inhibitor is a chemical that combines with the enzyme to make it inactive. It almost stops it completely. And most pharmaceutical drugs are inhibitors, stopping enzymes work. Right now, they are trying to create an enzyme inhibitor that will stop the coronavirus from replicating. And the way that it'll do that is this inhibitor will bind to the enzyme that helps make more enzyme, and when it makes more virus, and if it binds to that enzyme, the enzyme will stop working, and if it stops working, you will stop the virus from reproducing it, and then you will eradicate it from your body, hopefully. Okay, there are two types of inhibition. One is called competitive, and the other part is called non-competitive. The first one, competitive, is where the inhibitor binds to the active site and blocks it from the substrate from interacting. So this is a normal pathway where you have the substrate bind to the enzyme, forming transition state, forming the product. What an inhibitor does is it looks quite a bit like the substrate. So when they design these inhibitors, they will look almost exactly what the substrate is. So when they make an inhibitor, they find the chemical that it actually works, the substrate, and then they make a molecule that looks almost exactly like it, but can, and so it binds to the enzyme and it sticks in there, and it blocks the substrate from getting in there and essentially stopping the enzyme from making product. So the inhibitor competes for the active site. Okay, non-competitive inhibition is where the inhibitor will bind to another site beside the active site and make the enzyme inactive by changing its shape. So now the substrate can't bind anymore, the enzyme's turned off, can't make product. Okay, the last thing is using proteins for diagnostics in terms of diseases. So there are enzymes in our tissues that are involved with our organs working. If something happens to our organs, so maybe like your heart, if you have a heart attack, what will happen is your heart, those tissues will break down, and when they break down, they will release proteins, and maybe some of those proteins will be enzymes. So what doctors use as a diagnostic is they will measure enzyme levels in your blood, and if you have high levels of certain enzymes, it may tell if you have certain tissues damaged, because there's abundant of them, these enzymes, and the doctor would go, where did they come from? Since there's so many of them, where did they come from? And they know by looking at them where they probably come from. And so here's some examples, and I'm sure as you get into your nursing field you'll see more of these. But if there's, for instance, if there's a high level of lactic dehydrogenase, that may suggest that you had a heart attack, or etc. Okay, so that's it.